Hello and welcome to my talk about approximation algorithms for scheduling with class constraints. This is conjoint work with Klaus, Jansen and Marten Maack, and I am Alexandra Lassota. Before we go into our results, let us first have a look at what is class constraint scheduling. I think most of you are familiar with the classical scheduling problem, where we are given n jobs, each with a certain processing time, here displayed by the length of the bar. Now we want to schedule them, let's say, on 3 machines, and the goal is to minimize the make span, so the finishing time of the latest machine. The class constraint scheduling problem is pretty similar, but in addition, each job admits a class, and each machine has some class restriction. For example, each machine is only allowed to schedule jobs from 2 different classes. A schedule could look like this. And again, the goal is to find a schedule that minimizes the make span. So, what is known about the class constraint scheduling problem? There is a PTAS of the total number of classes as a constant. A PTAS is an algorithm that receives an accuracy factor epsilon greater 0 and computes a solution with only an additive error of epsilon times the optimal value, and does this in time encoding length to the power of some function in epsilon. Further, there is a PTAS if each class contains exactly 1 job. This problem is also known as the cardinality constraint problem, and obviously it's a subproblem to the class constraint scheduling. There are also various results for class constraint knapsack and class constraint bin packing. However, you see, there is nothing more for class constraint scheduling. In our work, we filled this gap. Our results are twofold. On the one side, we have constant approximation algorithms, which are simple and efficient, and they work for the non-preemptive case, the preemptive one, and the splittable one. In the non-preemptive case, you have to place the jobs as a whole, as we did in our example before. In the preemptive case, you are allowed to schedule a job on a machine, stop it, and then proceed on another machine in some time later. But here it is not allowed that job pieces belonging to the same job are scheduled in parallel. In the splittable case, however, you can just cut the jobs arbitrarily and place them wherever you want to. The other algorithms are the PTAS results for the general case, so where neither the classes nor the class restrictions on the machine is a constant. And these also work for the non-preemptive, preemptive, and the splittable case. In the following, I don't have the time to present all the results, so I want to present a high-level view on the constant approximation algorithm for the non-preemptive case and a high-level view on the PTAS, again for the non-preemptive case. So let us start with the constant approximation algorithm. Here are the main steps displayed we need, and I want to go through them step by step. But of course, at first we need to have an instant, which would look, for example, like this. And we may have 5 machines, each with the class restriction of 2, meaning we are only allowed to schedule jobs from at most 2 classes on each of the machines. So at first we start with the binary search for the optimal make span. This can be done easily, as we can estimate the lower and the upper bound. The lower bound equals just an equal distribution of the overall processing time. The upper bound in turn places the largest C classes on 1 machine. C is in our case 2, and the largest classes are 1 and 3. This picture is a little bit scaled down, but of course for a correct upper bound, we place the whole class 1 and the whole class 3 onto the machine. Okay, let's suppose we have now found some guess. Then the next step is to divide the classes larger than the current guess. We do so because we know if there is a solution with this guess, then we cannot place, for example, class 1 onto 1 machine. We're using some subroutine to group these classes now, such that each group is roughly of the size of the guess, and of course some rest if the class is not divided without rest. And yeah, we do a little error here, but roughly all of the classes are at most of the size of the guess. Now we are only interested in the groups. We're not interested in the particular jobs anymore. So we assign a new class here, and from now on we only handle the groups as a whole. Now we have to check if we haven't generated too many classes, meaning the guess was too low. So okay, we have generated 7 classes, and we know we have 5 machines, each with a class restriction of 2, so we can place up to 10 classes. And yeah, obviously, this guess holds. Let us now suppose we have done some iterations and this is the lowest guess we have found. So now we sort the classes regarding the processing times, which looks like this. And finally, we can allot them using round robin. That means we place the largest class into the first machine, the second largest class to the second machine, and so on, and then start again at the first machine. Obviously, as we equally distribute the jobs, we will satisfy the class restrictions, yielding a feasible schedule. Analyzing the error we do by grouping the jobs and by placing them using round robin, we get a 7/3 approximation algorithm for the non-preemptive case. Further, we can adapt our framework to also handle the preemptive case, which yields a 2 approximation. The ratio is better here, as we can group the jobs way simpler, as we can simply cut them at height of the guess. However, we have to handle the parallelism here. Using round robin, it could happen that job pieces belonging to the same jobs are placed in parallel, but by shifting them up a little bit, we handle this case. Then for the splittable case, this yields a 2 approximation algorithm, where the main obstacle was to handle large M. Before, it was not reasonable to have more machines than jobs, as we cannot place them in parallel. But here we are allowed to do so M can be arbitrarily larger than M. But by encoding classes which could occur together and sizes which could occur, we can also handle this case. So let us turn our attention to the PTAS now. Of course, at first we need to have an instance, which could, for example, look like this, where we have 3 classes for machines and a class restriction of 2. Now we start again with a binary search for the optimal make span, where, in contrast to before, the whole remaining algorithm is contained inside this binary search. The first new step is to group the jobs of each class, such that each class either contains only large jobs or exactly one small job. The distinguishing between large and small is here by some function in epsilon. We obtain this by gluing very small jobs to other jobs. So, for example, it could look like this. So class 1 and 2 only have large jobs, and class 3 has exactly one small job. The next step is to round the jobs a little bit, which introduces a small error, but in turn we obtain that we only have some function in epsilon many different processing times, and each of the processing time is integral. Now we come to the main step where we want to set up an n-fold ILP and solve it. What is an ILP again? So an integer linear program looks as follows. We have some objective function c, and we want to find a vector x such that c times x is maximized. But we have to do it under certain constraints given by some arbitrary constraint matrix A, such that the matrix A times x is equal to some right-hand side B. This problem in general is hard to solve, but we introduce n-fold ILPs. So it looks roughly the same, but the constraint matrix A is now a very certain block structure, which looks as follows. So we have blocks. These blocks themselves are arbitrary matrices, but they only occur at certain positions. So the whole constraint matrix A only has non-zero entries in the first few rows and the diagonal beneath. All other entries are 0. If the block dimensions are small, in our context it means some function in epsilon, then we can solve this n-fold ILP efficiently. So how do we want to tackle our problem now? We want to set up a so-called configuration ILP, which means that we have configurations which we give to machines such that all jobs are covered, and the configuration describes multiplicities of processing times, which could look, for example, like this. So we have a configuration which we will place onto one machine, which says, okay, we have the first processing time 2 times, the second processing time 3 times, and the fourth processing time exactly once. And now we can dissolve them into the jobs which have exactly this processing time. Doing this such straightforward sadly won't yield an n-fold structure and thus won't give us hope to obtain the running time we need for PTAS. So we introduce so-called configuration n-fold ILPs. So this is a setting as before. We have a configuration with processing times and we want to cover the jobs. but now we have to hierarchically layer the variables to obtain the desired enfold structure, which looks like this. So now our configurations we have are group sizes, so just placeholder of a certain size, and they have to cover the groups. A group, again, is only a placeholder for certain modules. The group itself is not in any way class dependent. These are really only placeholders for the modules. The modules in turn are what were configurations before. So they are processing time vectors, but only for exactly one class. And finally, we have to cover the jobs by the chosen modules. So overall, in setting the variables correctly, this yields that we won't assign too many classes onto a machine, and we won't exceed the make span. This is done by the sizes of the groups and modules and of the occurrences of different modules in the group. This is now an enfold ILP, and we can solve it efficiently. Having such a solution at hand, we can finally set up our schedule. And we do this just by dissolving it as displayed here. So we have chosen M configurations we need. These configurations are the group size placeholders. Then we have variables stating to which configuration we place which group, so we fill them in. Then we fill in the correct modules. And finally, we fill in the correct jobs, obtaining our schedule. So here are the results displayed for the PTAS with the corresponding running time. For the preemptive and the splittable case, we had to prove additionally some structural results, meaning if there is an optimal solution with value opt, then there exists an optimal solution with value opt plus epsilon times opt, where first, the number of job pieces generated for a job is bounded. Second, that the job pieces generated are at least of a certain processing time. And the third point is that these job pieces will only start at certain points in the schedule. Only if we can bound all these numbers, it is possible to set up an enfold ILP where the number of parameters and the number of variables is bounded and we can solve it efficiently. Further, of course, again, for the splittable case, we had to handle very large n. Again, we do so by encoding the schedule appropriately and have some insights about the steps before. So that was my talk on approximation algorithms for scheduling with class constraints. Thank you for your attention.